I'm a physics teacher first and a math teacher second. So now that you're armed with partial derivatives, we're going to take a moment and look at one of the coolest applications of that operation in the physical sciences. And it has to do with actually quantifying your error in a measurement. The idea is simple. Derivatives involve change. And if I have any function, we're going to use a one-dimensional function just to kind of demonstrate it first. If I'm looking at, sine of x, and we're looking at our angle from 0 to 90 degrees. So it looks something like this, where it's a big hump and it kind of shallows out towards the top. If I'm measuring an angle, the way that this function is structured is if I'm measuring an angle maybe at like 20 degrees and I make a little misstep, an error in measuring an angle down here, one way or the other in the angle, is going to give me a bigger change in the actual sine of the angle because the function is steeper in that region. If I were measuring an angle closer to 90, say like 85 degrees, and I make the same mistake in x, well, my difference in y isn't actually that big. And so functions are going to have different sensitivities to measurements depending on where you measure them. So sine of x gives larger change for small angles than at larger angles. In other words, because the slope of the sine function is shorter up here, I can be less careful when measuring in a weird sort of way. If I make the same error in measuring an 85-degree angle, my sine doesn't change that much than if I were to measure down here at 20, where a little bit of step left or right gives me a bigger jump due to that slope here. Now, if we think about a function in multivariables, for example, the volume of a cylinder. The volume of a cylinder is pi r squared. That's the circular base times the height of the cylinder. We're now, instead of an x and a y for our multivariable functions, we're using r and h to be two separate variables that both work together to give you that volume. Now, the volume, depending on how I measure r and measure h, can change in different ways. And this technique that we're going to develop today is going to help us quantify just how much that volume changes based off a little mistake in measuring the radius versus the height. If we take what we did over here in 1D, now our function, what I'm going to draw isn't exactly what the volume function here I have is, but in 3D, we no longer have a 1D curve, but now we have some kind of curved surface in space. So this 3D surface, and you can imagine picking a point. If I make a little mistake in measuring r, I might go a little bit this way and then follow the curve down, and that's where I end up. However, if I'm measuring the height of the cylinder on the other axis, well, there's a different curve that goes along with that, which might have a different slope along with it. And so if I make a mistake along this axis representing height, a little jump up or down is going to put me in a different position. And I'm going to get a different volume with this error in my radius and this error in my height. The amount of overall error, you can kind of think of it like a Pythagorean theorem sort of bit. Instead of doing, x and y or a and b, we look at how far we jump over along the radial axis. We look how far we jump along the height axis, and that puts us a total distance away in terms of the volume that we're going to consider. So we can think of like error as a distance. The larger the distance you are from the true value you're trying to measure, the more error that propagated through from these two measurements you made in your ultimate result. So let's get away from the abstract here and actually look at how we do this. Maybe you were just hired by Coca-Cola or something, and they want you to be in charge of can maintenance. So you have these cylindrical cans, and they're characterized by their height, how tall the can is, and the radius, r, the distance from the center of the can to the outside. You can measure this thing with a ruler. You can measure how high it is with the ruler. You can measure the radius with a ruler. and the ruler that can measure to the nearest millimeter. So it's a pretty good ruler, but it does have its limitations. So if we look at our ruler here, um, I know, here's 0, and each of these represents a millimeter. So if I measure a distance, maybe I get in between the two lines here. The best I can do is I have an error. I could maybe say something's right exactly in the center, but it's a little bit bigger than that, a little bit smaller than that. So, this 1 millimeter spacing gives me an error. We're going to use sigma to represent error. Get your giggles out now. So our measurement, sigma, is going to be equal to half that spacing, half a millimeter. In other words, when I measure the can, I can measure how tall the can is to the nearest millimeter, and then I might have error if I end up between the lines, plus or minus half a millimeter. Same thing with the radius. So both the error in our ability to measure the height of the can and the radius of the can have an error of half a millimeter. So the idea is that, going back to this Pythagorean theorem thing, thinking of error as a distance, the error in my volume, we're going to put that squared, is equal to the sum. I'm using the sum notation here. We only have 2 variables, but in general, you could have a function that has 3, 4, 100 variables in it, and all you're going to do is, for each possible thing you could measure, you're going to add up its contribution to its error here. So I'm going to use a generic variable x to represent a quantity. Here our x's are going to be r and h, but x is just generic here. So each measurement has its own error, sigma in x squared. So this represents the error in quantity x. We square that. The larger the error, if I had a worse ruler that only measured to the nearest centimeter, and then my error would be half a centimeter or 5 millimeters, then this sigma value would be larger. So the actual larger your uncertainty is, the bigger that this sigma is going to be. However, we're going to take this error and we're going to weight it by how much v depends on x. To represent that, we're going to look at the partial derivative of v, the volume, with respect to x. And yes, we're going to square that as well. So this gives how much v changes with respect to x. Depending on the functional dependence, for example, this radius here is squared, whereas the height is only linear. When you take the partial derivatives with respect to each of those things, you get a different formula for that partial derivative. And so you'll see that depending on how v depends on the radius and the height is going to affect how much those things ultimately affect the volume. And you can do some analysis where you'll see, hey, it turns out I need to be more careful when I measure R because that contributes to my error more. So we'll see that with the formula we're about to build. So what we're going to do, V depends on both R and H. We're going to use this formula, adding in square form here, or as they say fancifully, in quadrature. We're going to add them like that, and we're going to take the square root to get the total overall error in V. So our error in V, I guess I use delta here. I should use sigma to be consistent. Sorry, that'll be sigma V. Our sigma in V is going to be equal to the square root of our error in measuring R squared. And then we're going to take the partial derivative of V with respect to R. So we're going to get 2 pi R. The H is just a constant, so that stays there. And that's that partial derivative part squared. Then we're going to do the exact same thing, but now we're going to repeat it for H. So H has some amount of error squared. And then we're going to take the partial derivative of v with respect to h. V is just linear in h, and so everything that's not h is a constant that's going to be kept out front. So we get pi r squared squared. And this is our general formula. We can go through and simplify. We can pull things out that live on each term individually. So for example, we'll note that this error, we said we're using the same ruler to measure height and r. So sigma h is the same as sigma r. So I'm going to pull that out from the radical, and we'll just get, I'm going to call it just sigma now. Pi is squared on each of these terms, so we can pull out a pi. And then I get an r squared here and an r to the fourth here. So I can pull out an r squared from the radical. I get just an r out front. And then everything else stays on the inside. So this first term we get 4h squared plus r squared. So this formula here is a general expression that will help us, figure out how much r and height contribute to the overall error in being able to measure V. If I need these to be a certain volume, I want to know, do I have to pay more attention to R or do I have to pay more attention to H when I design these cans? This formula says no matter what the error, we said they're the same here, so it pulls it out, that R is actually going to contribute more. No matter what H is or R is out front here. So being a larger R is going to naturally contribute more error. So if I want to make sure I get these volumes right, it's going to be easier when the radius of the can is smaller. That's what this formula is telling us. So this is going to say volume more sensitive to radius. It says we get less error in V when R is small. It also says that when H is small too, but because R kind of dominates, it's the thing that gets pulled out of the radical, R will always contribute more than H does. So that's a consideration. If you're designing these cans, you need to make sure that the radius is on point. The height you probably also want to be on point, but you get to be a little more lax in that measurement. And do another example. I know basically all of my students at this point have done some sort of experiment where you've determined the gravitational acceleration, g, from free fall. When we did the error from that lab, if your teacher is anything like me, you probably had to look at, like, what was your error? Identify a source of error. And if you say human error, your teacher gets really angry at you. So you identify what your error is. If you're at a higher level, you might want to know, how does that error affect your measurement? Does it make your desired quantity too big or too small? You might be asked, if you do the experiment again, how would you fix those errors? Do multiple trials is the biggest way to do it. But you might think about something else about the experiment you could change to fix the error. Now we're going to take this error analysis to a whole new level, and you can actually figure out how big your error in your ability to measure G actually is. So the next level, we're leveling up here. How much error do you have in G? You can actually quantify how large your error is, how well you were able to measure G. In physics, you can measure G from free fall. You're just dropping an object from some height, y0. That's the initial height. You can measure how high that is with the ruler. So maybe you have an error in y0 of about, again, half a millimeter or 0.0005 meters. We can measure the time it takes for the object to hit the ground. So we have some sigma t. Maybe we can measure to the nearest quarter second. Maybe you're using a stopwatch. Human reaction time is about a quarter of a second. So, you you drop the ball and then you try to turn off the stopwatch right when it hits the ground, but you get plus or minus quarter of a second there. So your error in time is actually much larger naturally than your error ability to measure the height. So far it looks like time is going to be the big factor here. If we put this together with our equation of motion, we're going to eventually hit the ground. That's our final position. We start with our initial height, y0. If we're just dropping the object, its initial velocity is 0, and then we have minus 1/2 gt squared. So based off the initial height we're setting and the time it takes to fall, we can calculate g as 2y over t squared. So that's our formula for g. We were able to measure both the initial height and the time it takes to fall. And so now we have g as a function of those two variables. We have a multivariable function. We can take the partial derivatives of this to see how sensitive g is to small changes in both height and time. So let's set that up. So we can take the formula we just derived, g equals 2y0 over t squared, and we can look at how g changes with respect to each of these things. It is kind of weird thinking about g, which is usually a constant, 9.8, as having a derivative, but we're not looking at g as the constant. We're looking at how these factors affect our ability to measure g. So we're looking at how g changes in that regard. So we have to look at the partial of g with respect to y and the partial of g with respect to t. Well, it's just a constant, or linear in y, rather. And so the constants we get out front, 2 over t squared, are what we're left with. Now we have a t squared here, so we have kind of a t to the negative 2 power. So we're going to get negative 4y squared over t cubed as our derivative there. Now that we have both derivatives, we can use them in the formula. So sigma g is equal to the square root of our error in y squared times this derivative squared. So we're going to get 4 over t to the 4th plus dg dt was negative, but we're squaring it, so that does kind of go away. We have first the error in t squared times 16y0 squared over t to the 6th power. Now we can kind of take out the common terms. There's a 4 over t 4th that belongs to each of them. So we can pull that out, and we get 2 over t squared, all times the square root of sigma y squared plus sigma t squared times y over t quantity squared. So this formula is kind of interesting. It says, for one, if our error in y is really small, this term doesn't really contribute much at all. We have a much larger error in time, and then the fact that it's multiplied by this y squared means that, if y is too large, I might have a harder time measuring g because of that. So this term is dominant, the time error term, because not only is our error in t larger, but there's stuff over here that can compound how big that term is. However, something interesting kind of happens here. Since we have a t squared, 1 over t squared out front, that means that it tells us that as the time gets longer to fall, we're actually better able to measure g. So error decreases as time increases. And that makes sense. If it takes about 1/4 of a second to fall as my sigma there, if I'm only dropping this thing from like a height where it takes 1 second to fall, then 1/4 second's a pretty large percentage of that. So the error is much comparable to my measurement. However, if it takes much longer to fall, maybe I'm dropping this thing from the roof of a building where it's going to take 5, 6, 5 or 6 seconds to fall. Um, then now this quarter of a second becomes a smaller and smaller fraction. And as that time increases, it becomes less effective in my measurements. So thinking about this error formula gives us insight to how to get better data. We're probably not going to get the best measurement for G if we're dropping this thing from waist height. It's going to fall far too fast for our ability to actually, use the stopwatch and measure it. But if that time increases, we're going to actually, you know, this quarter of a second can become less and less relevant. Ideally, we'd like better measurements than the stopwatch, maybe a photo gate or something like that to really decrease the error in the first place. But the higher you're dropping it from and the longer it takes to fall, the less error you'll have in that regard. And so the time being out front contributes more than the fact that in order for the to take longer, you have to drop it from higher. So this term dominates the y squared that's inside the radical here. So that'll do it for error analysis. You now know how to take your lab reports to the next level. Thanks for joining in.